We are back with another lecture on fuel cells, hydrogen fuel cells. And today we will be talking about fuel cell modeling in the first part of this lecture. Then I guess we're going to have a break, hopefully. And then, since the first part requires a lot of attention, the second one is more informative and I think interesting, and we will talk about the system and the balance of plant in automotive hydrogen fuel cells. So we will check how a real fuel cell car works on the streets. Now, so in the first part today, I will introduce you to a modeling tool that I uploaded on BIP, on the BIP website of this course, that you can download obviously, and it is written in MATLAB, and you can use it to simulate fuel cells with a 1D or a 2D numerical model. I have it also here, so I will show you basically use it, but only just in a few cases. And this tool is given to you with two intentions. The first one, it could be useful if you decided to perform the project that is part of the evaluation of this course. And the second one, in order to go deeper, to get some insight into the effects of all the parameters that I presented you last time. So if you also want to check the effect of ion transport inside the catalyst layer, you can take the model, change this parameter, check what is the effect, and so on. Okay. So basically, so we start from what we said last time, and we said, okay, we can use a lambda model, so a simplified model, in order to have a kind of analytical equation that represents the operation of a fuel cell. But if we compare the simulation provided by this model with the real experiments that we get from real life, we see that there are a lot of differences, because the assumptions done in obtaining this analytical model are very strict. And so it is not a good tool if your intention is to have really insight into the operation of a fuel cell or a prediction of the performance of a real hydrogen fuel cell. And the reason was that in reality there are a lot of transport phenomena inside of a fuel cell that really affect the performance. And so we focused on mass transport, in particular oxygen transport inside the catalyst layer. We focused on ion transport, you remember, so the fact that ionic potential inside the catalyst layer is not constant, because you have an ohmic loss inside the catalyst layer because of proton ions moving inside of it and being a reactant. So basically, I introduced to you these new friends, but the problem was that we had just a kind of qualitative overview of this and some polarization curves. What we do today is the tough job, so we introduce the equations behind these assumptions, but unfortunately this differential equation, we cannot solve it on the blackboard, and we need a model. That's why today we're introducing a numerical model that can solve these equations. But the first part will be devoted to the introduction of these new equations that actually you do not have to solve, but it is important to know them in order to solve them, to use this model. Now, I need a pad. Sorry. Okay. So, these are the main assumptions of the model that I have given to you. This model is based on the continuum assumption. This hypothesis reveals that basically we consider a small volume in our analysis, in which, in this very small volume, we can consider this part of matter as being continuous. So there are some differential equations that can be solved for this small volume. And we consider a volume that is small enough in order to have a homogeneous value of all the properties inside of this volume. So for example, in each of them we will have one value of temperature, one value of electric potential, one value of ionic potential, and so on. Based on this hypothesis, we can use all the differential equations that are known under the hypothesis of continuum. For example, mass conservation, and so on, that you probably already have seen in other courses, like for example, heat and mass exchange, no? Isn't it? Heat and mass transfer. Okay. Now the point is, when you are dealing with continuum and we have a porous medium, this is a kind of tricky point. Because if you look at the porous medium inside, you have a strong heterogeneity within this medium, because there are some solid zones that separate the void where the fluid is flowing through. So if you look at a real resolved porous medium, you will see that the flow is going through all these fibers, all these sands, and so on. And so the operation that you have to do in averaging these is to go from this real situation with a continuum approach to this one that is represented here on the right. So to get rid of the real structure of the porous medium and to consider a kind of average fluxes, average velocity going through all of these porous media. But in doing so, the problem is that the transport properties will depend strongly on the structure of the porous media. This means, for example, that you have a certain heat conductivity through this, in this process that will depend a lot on the structure of the porous medium. You will have, for example, a diffusion of all the species through this porous medium, as well. This will depend on how this porous medium is done. And there are several parameters that affect this. There are several properties of the porous media that affect these parameters, and we'll check them later on in this analysis. But please remember that while applying the continuous hypothesis on a porous medium, you have to perform this operation that is called the volume average operation. So you consider to have a volume that includes several pores, and you have an average of several pores within your own volume. And the condition is the condition that is required is that the size of the pore, for sure, must be smaller than the volume that you're considering, in order to have a kind of average in your volume of several pores. Okay? Okay. Then, apart from this, in our 1D model, we are also considering other hypotheses that are required in order to have a numerical model that can solve the equation in a few seconds and not in minutes or hours. So, for simplicity, we decided to use an isothermal model, which means that in this model we have a constant temperature everywhere, and we neglect the fact that we are producing heat because of the electrochemical reactions, or we have condensation or evaporation that require an energy exchange. And we actually consider the temperature constant across our fuel cell, in the catalyst layers, in the membrane, in the gas diffusion layers. Then we are not resolving two-phase flow, so we neglect the formation of liquid water and the evaporation of liquid water. This, for sure, is a very important assumption that will affect our results, which means, for example, that at high current density, when we are producing a lot of water, our model we will not simulate very well the flooding of the porous media, and so the effect of limiting current changing because of the formation of liquid water and blocking of the gas diffusion layer. But unfortunately, we need this assumption because, as we said last time, two-phase flow requires a lot of coupling between different differential equations, and so it requires a really robust numerical method to be solved, giving you a lot of time for the solution, and in the end also a lot of numerical instability, which means you run your model and you get a lot of errors in the end. That message is telling you, okay, this time you will not get any result. So that's why we do not include the two-phase flow. The other point is the water content in the membrane. Last time we said, okay, ionic conductivity of the membrane depends on how much water I have in it. And we call this thing the water content. In order to have the effect of polymer dehydration under low relative humidity, you need to solve the water content in the membrane. But in this model, this effect is not included as well. And the reason is that I did not have the time to upload the model. Maybe next year I will include it, let's say. But also because it's giving you a lot of coupling factors, so you're changing the relative humidity and a lot of other parameters are changing at the same time. So I think that for didactic reasons, for deductive use is not the best, because you need also to be very experienced with the base model in order to include also this advanced equation. And finally, we have the geometrical assumptions. Here is how the fuel cell is looking like. Do you remember this? So we have now two coordinates. One is the X coordinate that is going through the membrane, the catalyst layer, and so on. And this is the major one, and we will mostly focus on these coordinates. So, at least in the first part of my talk, I will discuss a 1D, a monodimensional model, looking at how properties change through the catalyst layer and membrane assembly. Okay? Okay. Then later on, we will talk about the other coordinates, so the effect of the channel direction and how the operating condition evolve along the channel. Okay. Probably remember that in the three-dimensional equations of mass conservation, for example, you have the divergence of the flux. Okay, that is a numerical operator that has clear meaning in 3D. Since we are considering now a monodimensional model, you have to remember that the divergence of the flux is basically the derivative of the flux in the direction xx with respect to the coordinate x. Okay, so it's basically the derivative of the flux. Also, for example, in Ohm's law or in Fick's law, you remember that you have that the flux is proportional to the gradient of a certain property. And please remember that in 3D the gradient is a vector. In 1D, for sure, it is a vector as well, but we have just to consider one direction, and so the direction of the gradient is not important, and the intensity of the gradient is the derivative of this property, in this case the potential, with respect to the coordinate. So, from a very simplistic point of view, basically both the divergence and the gradient are giving you a derivative of this property with respect to the coordinate. But please remember that they come from very different concepts, okay? Okay. If you're okay with this, any questions? No? Okay. We can go through the model. The model is included in a folder. Okay, there is a compressed folder, for sure. You can decompress this folder and you get this. And you see that there are some files that you cannot access that are called .p. These ones are protected files in MATLAB, so they are encrypted and you cannot open them, but you do not need them. Instead, you need all the files that are .m. Okay. The main file for the model is called mod manager. And if you run this, the model will run, basically. So, in mod manager, you have the file running, you have the model running. Well, instead, you have also three other relevant files that we will check later on. One is the modeling options. And here you have the options. You can choose a 1D model or a 2D model to simulate the impedance spectroscopy or not. Here you have the mod param. In here you have all the physical parameter and all the operating condition. So if you want to simulate polarization curve with 100% oxygen, more fraction, you want to simulate a case with 160 degrees C, you can do it. You just change the parameters here. Finally, mod plots is just plotting the results, and this file also is open so that you can change the plots. Basically, you can work on this MATLAB file. Okay, now let's go to the equations. Let's look at the polymer membrane. In the membrane, we have ion transport, and we have to consider the conservation of charge. So ion is H plus, hydrogen plus ion. This one will conserve through the membrane. We are in 1D, so the divergence of the current will be 0 because in the membrane you are not producing protons, they're just transported, okay? And also we are in steady state, so there is no storage of protons inside the membrane. Because of this, the derivative of the current, of the hydrogen ion current, so the ionic current, is 0 inside the membrane, which equation you already knew from previous lectures. In order to solve this equation, generally, you need to couple it with another one that describes the transport of ions inside the membrane, giving you a relation between the ion current and the potential. The law we use in this case is Ohm's law for ion transport, because, as we saw in previous lectures, migration is basically neglected in fuel cells, where the polymer backbones cannot move freely within the polymer, but the polymer is stuck in the matrix. Okay, so basically with the ion conservation and Ohm's law for ion transport, you can solve the membrane problem, and the result that you will get is the ionic potential, pH, how it is distributed across the membrane. Okay. Then you need to solve the cathode and anode catalyst layers, which are not interfaces, but have a spatial distribution of properties. In order to do this, you have to include ion conservation also for the catalyst layer itself. And in this case, the divergence of the current inside the catalyst layer, of ion current inside the catalyst layer, is not 0, because we are producing proton or consuming proton based on the electrochemical reactions. At the anode, we are producing protons, okay, because hydrogen is going through an oxidation. Instead, at the cathode, we are consuming proton ions because of the oxygen reduction reaction. Also, in order to simulate impedance spectroscopy, we included also this transient term that is due to the double layer. So we have to consider the fact that we can accumulate protons and electrons inside the catalyst layer at the interface between the ionomer and the carbon. So where we have an electronic conductor in contact with an ionic conductor, we have an interface that acts as a capacitor, and in the conservation of charge, we have to also include this transient term. For sure, this equation, as done before, must be coupled with the Ohm's law inside the catalyst layer, which will tell us that the current is proportional to the gradient of the ionic potential inside the catalyst layer with a minus sign and a conductivity parameter. This ionic conductivity that we introduced also in our previous lecture will be for sure different from the one we have in the membrane, because ion transport inside the membrane is different from the ion transport we have in the catalyst layer. Very similar equations will apply for the charge conservation. We are also producing and consuming electrons inside the catalyst layer, so the divergence of the current will be equal to the consumption or production of electrons that we have because of the electrochemical reactions, as well as the double layer current accumulating inside the catalyst layer. Is it clear? Okay, and for sure, in the graphite, we have Ohm's law that will describe the relation between the electric potential, PE, and the electric current inside the catalyst layer. Okay, now, if things now were simpler, now they become a little bit more complex. Here we have instead we move from all the electrical quantities to the mass quantities. And here we have mass conservation that is written here on a mole basis. You have, in this case, n, that is for me the mole flux of species going through the GDL on the x coordinate, okay? Okay. For this mass flow, n, for the species E, I, we have the divergence of the flux is proportional, is equal to the mass that we're consuming because of the electrochemical reaction, okay? So, for example, at the anode, in the anode catalyst layer, Si will be negative because we are for hydrogen, because we are consuming hydrogen at the anode side. So, on the mole conservation of hydrogen, we will have a consumption for sure of this species that will appear here as a sink term because of the oxidation reaction. As well as we have to consider the fact that we can store mass inside our porous media, so that we have also to include this transient term. This equation is solved for all the species that we need. In this case, at the cathode we have oxygen, nitrogen, and water, while at the anode side we have just hydrogen and water. Okay? Okay. Here, for example, is how this equation looks like for oxygen in the catalyst layer, isn't it? Where the divergence of oxygen is equal to the consumption of oxygen due to the electrochemical reaction, plus this this accumulation of oxygen inside the pores of the catalyst layer. Okay, previously you had this equation only for the gas diffusion layer. Now we have it also for the microporous layer. We have it also for the catalyst layer. Now, generally, you are used to combine this conservation equation with fixed law of diffusion in order to have a relation between the mass flow and the concentration gradient inside of your gas, your species, your liquid, whatever it is, your volume. Instead, when you have a multi-component diffusion, fixed law does not hold anymore, because the main assumption is that all the species are diluted. And this is not true for all the species we are considering in our case. For example, oxygen and water, nitrogen and water are present at very high mole fractions. They are about 50% of the gas in the gas composition. They could be up to 50% in the gas composition. This means that fixed law of diffusion must be left over, and we must move now to a different law that is called Stefan-Maxwell diffusion instead of fixed law. That basically is based on this equation that is slightly more complex. The important idea behind is that there is always a gradient of the concentration of the species that is diffusion that is proportional to the fluxes of all the species that are diffusing inside the porous medium. So in this case, if we are considering the gradient of oxygen concentration, for example, it will not just be proportional to the oxygen flux, but also to water flux or nitrogen flux, because of a kind of drag effect of the other species bringing also oxygen while diffusing. And we see here that the fixed diffusion is now substituted by another parameter that is the molecular diffusivity of the species in the medium that we are considering. So instead of having just one diffusion coefficient, in this case, for example, for oxygen, we have two. We have to measure the diffusion of water versus oxygen and the diffusion of nitrogen versus oxygen in order to have the possibility to write this equation. Okay? Okay. Finally, when in porous media, there is another kind of diffusion that is called Knudsen diffusion. This kind of diffusion becomes important when the pore size becomes very small.
Hello.
Now,
Pore size.
talk more about. Sorry? So we also have, basically, in our equation, also the effect of Knudsen diffusion as an additional term compared to molecular diffusion. In fact, for molecular diffusion, generally, we have the transport is due to the interaction of a gas molecule of a species I with another species. For example, oxygen diffusing in water. The most important interaction you have is the one of oxygen with water while diffusing as a ball across the gas. And this is the case on the right side. So you have in this case a porous media with a pore size that is very large, so the interaction of the gas with the walls is not important. Instead, when the typical size of the pore becomes very small, you have this additional effect of Knudsen diffusion that accounts for the interaction of the molecule with the walls of the pore. And the question is, when do we have to consider also Knudsen diffusion? Here you have a plot taken from the paper. In this case you see on the x-axis the typical pore size of fuel cell media, moving from around 100 micron to about 1 nanometer. Okay, so it's a logarithmic scale going through a very large difference in pore size. And what you see that the gas diffusion layer typically has a size has a pore size above 10 micron. So the last almost is present in this region. In this case, the interaction between the molecules, so the mean free path of the molecule, is much smaller compared to the pore size. So the dominant mechanism for diffusion is molecular diffusion, and inside of the gas diffusion layer, the contribution of the Knudsen diffusion is almost zero, so negligible. But this is not true for the microporous layer and the catalyst layer, which typical size is much smaller, in the order of a few microns for the microporous layer, or hundreds or less of hundreds of nanometers for the catalyst layer. And you see actually that in the catalyst layer, generally the dominant mechanism for oxygen diffusion is Knudsen diffusion. So, since the pores are in the order of 50 nanometers, what happens is that the molecular oxygen mean free path is comparable to these 50 nanometers, so you have to account also of the interaction of the oxygen with the pore walls. So, the key point is, if you neglect Knudsen diffusion, you will not have a correct representation of oxygen transport inside the catalyst layer. That's why I had to include it in the model. There are some simplified laws that gives you an approximation of how much the Knudsen diffusion could be for a gas diffusing inside a small pore. And you see that this diffusivity is basically proportional to the diameter of the pore or the pore size. Okay? So this equation is also implemented in the model in order to have an estimation of the Knudsen diffusion for the porous media. But for sure you need to know the typical pore size of your catalyst layer, or at least a guess. Oops. Now,
Excuse me?
yes.
Previously. What are the terms epsilon, tau, and those kind of terms?
Yes, this is a correction for the porous medium that I will introduce probably later on if I remember well. Okay. It will come later. Now, just a few words about the kinetics of the oxygen reduction reaction. Last time we said that if you want to have an interpretation of the experimental data, you need to account for the coverage of platinum because of platinum oxides. Okay? So this process is occurring at high potential, above 0.8 volt. We have that the fraction of free platinum goes from 100% to 20-10%. In order to account for this, I took this estimation from literature, based on some reasoning on the platinum oxidations, and I introduced to you just to let you know that in the model you have the formation of platinum oxides at high potential that will change the kinetics of the reaction. So if you're looking for a pure logarithmic trend, this is not what you will see in the model, because at high potential you will have an effective activity of the catalyst that will be lower because of the formation of this platinum oxide. Instead, differently from what we did in the lumped model, we will consider the hydrogen oxidation reaction kinetics. Also in this case, we will use the Butler-Volmer equation. Remember that we use Butler-Volmer equation when the reaction is giving you an overpotential that is generally not very high. So you have to account in your reaction rate both for the forward and the backward reaction rates. Okay? Instead, in Tafel law, you said I'm far from equilibrium, I can neglect one of them. Okay. Now, we can open our model manager. We go in our folder. We take the mod manager file. We can run this file, for example, and we see that the model MATLAB starts to solve our model. What it's telling you is that we are solving, in this case, a steady state. So we are simulating a polarization curve. Every step is a different potential that our model is simulating. I decided to just simulate 10 points in order to avoid to stay here for hours. It generally starts from high potential. So the first part is the low current part of the polarization curve, and you see that it is very fast to solve. Instead, when you go at high current density, the model requires a lot of time for the solution. And this is because transport phenomena are more important at high current density, so the properties is having a clear gradient across the media, and that's requiring you a lot of time for the solution. So this is the result of the model. You have basically the voltage of the cell, that is the black curve, versus the current density. And also you have the contribution of the cathode side, that is always the blue line. And you see that the potential of the cathode is higher compared to the voltage of the fuel cells, because you have other losses, isn't it? In fact, you have the membrane loss that is reproduced here in green. And you have the hydrogen contribution, in our case, that is the red curve. Here is the anode potential, so you have to consider this as basically the contribution of the anode, or the loss of the anode that is given in the polarization curve. Okay? If you look at the equations, what you get is that the voltage, that is the difference between the electronic potential at the cathode side minus the electronic potential at the anode side, is decomposed in three parts: the cathode potential minus the anode potential minus this membrane ohmic loss, as you already saw in the previous lectures. Okay? So this is basically the output of the model when you simulate a polarization curve. Now, this will come later. Probably you want to compare your model with the lumped model. Okay? So here I have already saved the lumped model. I can show you. As expected, the lumped model is the dashed line. So you see that when we introduce additional transport phenomena, like ion transport inside the catalyst layer and so on, we have an additional loss. So from our very simple model to the new one, we confirm, as we saw in the last lecture, that we have an additional loss that becomes more important at high current density. Okay? So at high current density, we have a relevant divergence between the simplified model and our 1D model because of additional phenomena that we are considering. Okay. Then what is also interesting is that if we look at the anode, basically, in the lumped model, in this case for sure, I included also the hydrogen kinetics, but I neglected all the transport phenomena across the anode catalyst layer. Okay? So we have the anode catalyst layer that is giving you a uniform operating condition, and you see that the difference between the simplified model and the model with all the transport mechanisms really changes the situation of the anode. So in the first case, the anode was giving you almost zero contribution, but if you include also ion transport, inside ion catalyst layer, you also have an effect not negligible of anode transport that become visible, obviously, at high Coulomb densities. Okay, so the assumption of neglecting the anode contribution makes sense if we are not looking for a result with an accuracy in the order of less than 10 millivolts. Otherwise, if we want a high accuracy of our model, we have also to include the effect of the anode. Okay? Now, apart from this, the model is giving you also other plots that give you an idea of what's going on inside the fuel cell. There are two major plots. One is dealing with all the mass properties. The other one is dealing with all the potentials. Okay, let's focus with the first one. These plots are giving you a spatial distribution of all the fluxes and the mole fractions of our species according to the model simulation. All the media are supposed to be with a length of 1, with a thickness of 1. So the gas diffusion layer at the thickness of 1, the microporous layer at the thickness of 1, the catalyst layer at the thickness of 1. This is because of the very different size of the three media. Otherwise, it would be almost impossible to see what's going on in the catalyst layer. Okay, so for the zooming effect, we decided to keep just a uniform thickness of 1 in the plot. Now, what you see here is on the left side you have the anode side, on the right side you have the cathode side. Here, for example, you have fluxes going into the fuel cell. On the anode side you have hydrogen. You have hydrogen, that is the curve at 0.5, that is moving inside the gas diffusion layer with a positive flux, so directed in the direction of the coordinate, going into the gas diffusion layer, the microporous layer, and you see that the hydrogen flux goes down inside the catalyst layer because it is consumed, and for sure on the membrane we have a condition of 0 hydrogen flux going in. So the flux of hydrogen must be 0 on the membrane because it is a wall for species transport. Here you have the mole fraction resulting because of this process. The one here is the hydrogen mole fraction, and the other below is the water mole fraction, how it changes within the porous medium. And what you see here on the anode side is that mole fractions are more or less constant, uniform, because hydrogen has a very high diffusivity, so transport inside the gas diffusion layer is very easy for the hydrogen. Please.
So we're not consider a crossover, right?
Yes, we're not considering crossover.
Okay.
But even if you are considering crossover, this contribution would be very small. So instead of having 0, you would have a very small number compared to the hydrogen flux. Okay, now we look at the cathode side. On the cathode side, we have 3 species. One is nitrogen, that is not moving through the gas diffusion layer because it's not consumed by the chemical reaction, and is the flux that is set as 0 through all the media. And then we have one species having a positive flux and another species having a negative flux. Okay? Considering the coordinate is going in this direction, water is going out, so from left to right. Instead, oxygen has a negative flux because it's going from the channel into the gas diffusion layer and so on. And what you see, for example, for oxygen is that it's diffusing across this medium, and then it is consumed in the catalyst layer, and we have 0 oxygen flux at the membrane side. We also see that the intensity of the flux of oxygen is half of the intensity of the flux of water, because water produced is double oxygen consumed on a molar basis, for sure. And but you probably, what I have to tell you is that this number is non-dimensional, okay? And the dimensional, basically all the fluxes are set as non-dimensional according to this very simple equation. So we consider a reference flux of current divided by the Faraday constant as a reference flux, okay? So for example, for water, this number will be 0.5. because it is 1 divided 2 electrons produced by each proton consumed. Okay? Now, here we look at the potentials. Basically, once you understood that plot, this one is very easy, and the current you have inside your media. We neglect the currents inside the gas diffusion layer. Now we care only for the catalyst layer at anode, the membrane, and the cathode side. Here you have just to remember that you have an electron current and an ion current. So you have two types of current. The green here is the electron current, so the electrons, okay, which is positive because electron has a negative charge, okay, so the current is going into the catalyst layer. And you see that this current is going basically to 0 at the membrane because electrons cannot go in the membrane, okay? Also, you see that the current of protons is 0 on the GDL side because on this side protons cannot go further. Instead, it is increasing as a peak into the membrane. So we are producing proton at the anodes, they go into the membrane and they are consumed back at the cathode. Net result of proton going in or out your cell is 0, okay? Just electrons are going in the external circuit. If you couple with this with Ohm law, you will not be surprised to have a potential gradient inside the membrane that goes down from left to right because protons are going from left to right. In the Ohm's law we have the minus sign between the flux, the current, and the gradient. So in order to have the positive current going from left to right, we have to have decline in the ohmic potential, in the ionic potential inside the membrane. Okay? And the same you have also for electron transport, the electric potential, even though we know that it is not so relevant for real fuel cells. Okay? Is it clear? Okay. Now, with this model you can also simulate the impedance spectroscopy. How can you do this? You open your model, you select a file that is called mode options. In mode options there is an options.eis, and you set this number to 1. You run your model, and your model will first solve a steady state, and then will apply one frequency by a time in order to perform the impedance spectrum. So first we'll apply 1 MHz frequency, 100 kHz, 1 kHz, 100 Hz, 10 Hz, 1 Hz, and so on. So you will get the impedance at different frequencies. In this case, I decided to simulate 50 frequencies in order to have a clear spectrum and not something quite scattered. Oh, no. And what you get here is a plot. This is the case I simulated, so the current density was around 1.25 amp per square centimeter. I decided to simulate the spectrum in this condition, where I have 0.6 volt. And the resulting impedance is this one, that you can get from your model. Please remember that this one is the Nyquist plot. Here we have the imaginary part of the spectrum and the real part of the spectrum as a function of frequency. Okay? Now, we go back to the presentation. So what you get basically is here, and as done for the polarization curve, you have the complete spectrum, the complete impedance. That is basically the electrical series of the cathode, the anode, and the membrane impedance. So basically it's the sum of these three impedances that you simulated. And here you have also the contribution of each side in order to get some insight inside of the meaning of impedance. And the blue contribution is always the cathode, the red contribution is the anode, and the membrane is giving you this high frequency resistance, as we said previously. So, if in my model, for example, I would change the ionic conductivity of the membrane, the only change that I should observe is a change in this resistance going higher or lower because I'm changing a property of the membrane. Okay? And what you will see is also the effect on the whole spectrum. Then, okay, so okay, as done for the now. If you want to change the condition where you are performing in which you are performing your impedance spectroscopy, you have to look for the mod param file. In this file, all the parameters are written. There is a part dealing with the polarization curve and the impedance spectroscopy. Here, by changing this parameter, you will change the simulation you are performing. For example, looking at the IS, this is the number of frequencies we are simulating, 50. They are logarithmically spaced. Then we have basically for the polarization curve, you see that we are simulating 10 points. So by changing these numbers, you can have a faster simulation or a slower simulation by adding points to your polarization curve. Instead, in the EIS, I just simulate one spectrum by a time. In this case, I have the possibility to simulate my impedance spectrum controlling the current or controlling the potential. This is changed in our model by changing one options, because in fuel cells generally we distinguish the so-called potentiostatic operation from the galvanostatic operation. In fact, in the potentiostatic operation we are setting the voltage of the fuel cell, and the result of the model will be the current density. So we are running our cell at 0.6 volt. The model will tell us 1.2 amp per square centimeter. This is done in the model with this option by setting 1D underscore pot. Instead, to have a galvanostatic simulation, this means that I want to know the voltage of my fuel cells at 2 amp per square centimeter. So I select 1D galvanostatic options, and then in this case I'm setting the current density that I want. Okay? For sure the result will be the same. Okay? So the same polarization curve you will obtain whether you have a potentiostatic or a galvanostatic condition, because the equations and the parameters are not changing, it's just the way you solve it. In the model, this is done in the mod options. The first option is options.dim, and you can choose, in this case I was simulating with a 1D potentiostatic condition. You can change it with also 1D galvanostatic condition according to what I said before. Is this clear? Okay. Okay. Now, regarding the effective properties that we have in our porous media. Since we are dealing with porous media, as we said before, the real diffusion coefficient, called effective diffusion coefficient, and the conductivities, called effective conductivities, are not bulk properties. I mean, I have a certain diffusion coefficient for oxygen in water, when we have just 100% gas phase. Instead, inside the pores of inside the pores of a porous medium, these diffusion properties will change. Will change because the void space will be less than 100%, and this property is called the porosity. The porosity of the porous medium is the pore volume divided the overall volume of the medium. So, for example, a porosity of 50% means that 50% of the volume is free for diffusion, the other 50% is occupied by a solid, by the fibers of the GDL. By reducing the porosity, you are basically reducing the area that is available for diffusion. So, you are linearly decreasing the diffusivity when you are reducing the porosity. Okay? Okay. But still there is another effect that is called the tortuosity. The tortuosity, in fact, gives you an idea of how long is the effective path for diffusion compared to the straight line. So it is defined geometrically as the ratio between the blue curve, the length of the blue curve divided by the length of the red curve. Okay? Because we have oxygen that will not go directly through this medium, but has to go all around the fibers, we will have a diffusion path that is longer, and this will hinder basically diffusion. This geometrical parameter that is called the tortuosity is also affecting the effective diffusion coefficient. The longer the path, the lower the diffusion coefficient. So we have to divide the bulk diffusivity by the tortuosity in order to account for the effect of this porous medium. Okay? The same happens not just for diffusion of gases, but also for charge transport. Okay? Because for the ion in the catalyst layer, not 100% of the volume is available for ion transport, but only the ionomer itself. So the same situation will occur, and basically the effective conductivity will depend on how much ionomer you put inside your catalyst layer. The more you put, the higher the conductivity you will have, because the proton transport will go more linearly more straight through the catalyst layer, and also the volume available for ion transport will be higher. Okay? So remember that the transport properties inside these porous media are not something that you can measure in the lab easily. You can only get from real operation of the system. You cannot say a priori how much this effective property will be. Okay? Okay. Then, if you want, you can perform a sensitivity analysis on the model parameters. So you take your model. For example, you change, I selected here some parameters that could be relevant, also if you want to get insight in what we said in our previous lecture. For example, you can change the effective diffusion coefficient in the gas diffusion layer by changing the tortuosity, here tau, the Greek letter I used before, the tortuosity of the gas diffusion layer at the cathode side. All these properties are indicated and commented in the mod param file, so you can get exactly what they are, and they are included in the equations that I have shown before. So basically, you have all the information. So if you want, for example, to reduce by a factor of 10 the tortuosity of the gas diffusion layer, you can change this number inside and check what is the effect. Okay? Also, you can do this both on the polarization curve and in the impedance spectroscopy and get additional information. This is what I did before. So basically, the comparison of the simplified model with the new model regarding the polarization curve. Here instead, you have the comparison of both models considering impedance spectroscopy. You see, as we saw in our previous lecture, that there is a significant difference between the spectra, the one simulated by the 1D model and the one obtained by the simplified model. At the cathode side, we see a large difference in the high frequency region because of the appearance of this linear branch that is connected, linked to the ion transport inside the catalyst layer. You remember this? Also, we have that there is a kind of distortion of the spectrum in other points, and this is because this model is quite complex. So we have the superimposition of several effects. Okay? If we have both ion transport limitation, oxygen transport limitations, the resulting will be basically a very complex result that is quite difficult to interpret without a model. That's why from experiments generally there are a lot of issues in the interpretation of the impedance spectroscopy. Here you have the case of the anode side. You see that in the real model the impedance of the anode gets bigger, and this makes sense because the impedance itself is a sense for a voltage loss. Okay, so the bigger impedance is the higher the loss at that is attributed to this phenomenon, in this case the ion, the hydrogen oxidation. So in the real model, we have that the anode contribution is not negligible because the impedance, even though small, is not zero. And we see a clear shape of this spectrum with a linear branch at high frequencies, indicating that at the anode side we have problems of ion transport inside the anode catalyst layer. Okay? Okay. Now, so basically then you can use your model to predict what is the effect of the operating conditions and check, for example, the effect of gas pressure, the effect of temperature, the effect of oxygen transfer pressure. So to change the operating condition of your fuel cell and check what is the real response of the system. And the question could be, okay, do I have any advantage in increasing gas pressure in my car? Can I get higher power density or no? What if I reduce or increase oxygen partial pressure? What do I get? And so on. Basically, what we get from this model, the most important effects are the effect of gas pressure and the effect of oxygen partial pressure. Because to check the effect of relative humidity, this model is not adequate because we cannot reproduce both water flooding, liquid water flooding, and the membrane dehydration. So the effect of relative humidity is not the same that you have in the experiment, okay? Because of the model's assumption. Okay. So you take your model, for example. You go in the mod param. There is a part of this code where you have the operative condition. In this case, here you have all the operative conditions that you need. What you can say, for example, is to change the mole fraction of oxygen inside your model. Instead of the value you have in air, around 21%, you can set 100%. And you're feeding, in this case, pure oxygen, or 1%. And you're feeding a oxygen depleted flow. What you get from the polarization curve is an indication of the fact that at high oxygen concentration, so for example with pure oxygen, your polarization curve will have a clear shape of a logarithmic trend, then declining into a linear trend. Because when you increase the oxygen concentration, you are also increasing the limiting current. You remember from last lecture that the limiting current was substantially proportional to the concentration or the activity of oxygen that you are feeding in the channel. So basically what you observe here is that under pure oxygen operation you do not have limitation from mass transfer because oxygen is very highly available in your system. While instead, if you decrease the concentration of oxygen, you will basically see that the performance go down very, very soon because because the limiting current basically has changed in your operation. That's what people generally perform in the laboratory. If you want to check the kinetics of your material, you perform a polarization curve under hydrogen or oxygen. In this case, you will get rid of all the mass transport effect and you will check just the effect of kinetics and ohmic transport. Instead, if you are interested to analyze the mass transport of your material, you can perform a test at very low oxygen concentration, for example 1% oxygen concentration. In this case, you will have a clear measurement of the limiting current. Okay, so this is typically what people do in their master thesis in our lab. Then another parameter that is the cathode pressure, that is important in the last part of our lecture when we will talk about the Toyota Mirai. You see that by increasing the pressure from 1 to 3, there is basically a shift of your polarization curve at full potential. So we have an increase of performance at low potential because the oxygen activity is becoming higher. okay? It's proportional to the pressure of your system. But also because hydrogen pressure is increasing as well. Remember that in a fuel cell, you have to pressurize both anode and cathode in order to avoid a high pressure difference from one side to the other that could damage the membrane, mechanically damage the membrane. So in this case, you have to pressurize both anode and cathode, and you get an increase, an improvement of kinetics of both electrodes. That will result in kinetics and thermodynamics of both electrodes. That will give you a positive effect at low current density. Instead, in the high current density region, you have also an increase of the power density, so the limiting current is shifting at higher currents, and this is basically because the limiting current itself is also increasing. Okay? Okay. So basically, if you want to increase the power in your car, you have to increase the pressure. Considering that you cannot increase the oxygen mole fraction. Okay? You cannot take air and then remove nitrogen on the car. Okay, well instead, for example, in submarines, they need both a storage for hydrogen and oxygen. So in this case, they are just performing operation in pure hydrogen and pure oxygen. Okay, now just a couple of words instead on the 2D model, because what we discussed so far is just the effect of all the properties across the catalyst layer, across the membrane, across the gas diffusion layer. Now we also need to perform some calculations on what is the effect of the channel coordinate. As you saw previously in Andrea's lecture, you see that because of the consumption of reactants, the composition of gases is changing from inlet to outlet of the cell. Okay, you're consuming oxygen, so you feed the pure air, but at the outlet you have just 10% oxygen mole fraction. Okay, and the same happens for hydrogen, water, and whatever it is. So, now we have to include another spatial coordinate, that is the Z coordinate, or the channel coordinate. In this case, so your model will give you a result that is something like this. So on one side you have hydrogen and air entering into your fuel cell. You are consuming hydrogen, consuming oxygen, producing water. So basically, the molar flow of this species is decreasing or increasing along the channel. It's no more constant because of the consumption of reduction. Here you have what you can get from your model if you set the condition to the galvanostatic, but actually this model, numerical model, takes a lot of time for the solution, so probably you do not need it for this course. What you see in this case is the molar flow of water entering your fuel cell at the cathode side is those increasing because of water produced because of oxygen reduction reaction. Instead, you see that the oxygen molar flow is going down because you are consuming oxygen. The assumption that you are applying here is the plug flow model. Do you remember this? So we're neglecting basically the diffusion of oxygen along the channel because the Becquerel number is very high, and so we have a very high velocity that is much higher than the diffusion velocity, and we can neglect backward diffusion of oxygen along the channel because the speed is the velocity of the gas is very high. And so we get basically what people call the plug flow model. According to this model, basically the molar flow that you have is the sum of the oxygen, the nitrogen, and the water flow that you have. Basically, you are summing the flux, the flow of all the species going through your channel. Okay? Okay. Yes?
Can you repeat the part of the Becquerel number you mentioned?
Yes, basically when you have a very high flow rate, okay? When you have a very high velocity in the channels, because you are feeding a very high flow rate in very narrow channels, so the velocity is in the order of 10-20 meters per second. In this case, you can neglect the diffusion or of oxygen, you have a gradient of oxygen concentration along the channel for sure, which should give you a diffusion of oxygen or water. This thing we can neglect because the diffusion velocity is much lower than 1 meter per second. So the contribution in our reactor will basically be zero. Okay? Now, the parameter that allow you to estimate the effect, how non-uniform your operation is along the channel, is the stoichiometry. The stoichiometry is the ratio between the gas that you're feeding divided the gas that you're consuming. And we have one stoichiometry at the cathode side and one value of stoichiometry at the anode side. Okay? Okay, so for example, in the case of oxygen, the stoichiometric flow of oxygen, as you remember, is proportional to the current that you're drawing in your system divided for F, F being the Faraday's constant. So, when you're operating your system at constant stoichiometry, if you increase the current, you are increasing the flow that you are feeding in order to have a constant consumption of your reactant. Typical values of stoichiometry are between 1.5 and 2.5 for typical system. So, which means, for example, at the cathode that we are feeding 1.5 times the oxygen that we need. So 50% more than the oxygen that we need. Okay? Okay, and the same for sure we can do at the anode side. Now, what we see, if we are decreasing the stoichiometry in our model, going from a 1D case, the 1D case will be the limiting case when we have infinite stoichiometry. Because if you have infinite stoichiometry, the condition along the channel will not change anymore. The flow will be so high that you don't care about how much oxygen or hydrogen or water you consume, okay, or produce. Because basically the consumption will have no effect on the net mass balance, and what you are feeding is exactly what you are getting at the out. So in the case of infinite stoichiometry, basically we are going back to the potential static model. This is stoichiometry infinite. Okay, instead, when you decrease the stoichiometry, you observe that the oxygen concentration, that is the one set by air, humidified air at the inlet of your fuel cell, basically will go down along the channel because of oxygen consumption, and this change will be more relevant when you have a low value of stoichiometry. Okay? So, under low stoichiometry, the oxygen concentration will be very different from inlet to outlet, being very low at the outlet. And the same happens for water. Since we are producing water, if you are feeding a very high flow, so a very high stoichiometry, basically, the water concentration will have a small change from inlet to outlet. Instead, when you reduce the stoichiometry, you will move to the continuous line, and there will be a very significant change of water activity or water concentration from the inlet to the outlet. Okay? You are producing water at the cathode side, so if you reduce the stoichiometry, you have a high, small flow, small fraction of water at the outlet. This means basically that your performance will be lower when you reduce the stoichiometry. This happens because the oxygen mole fraction will not be constant at 21% or whatever it is all along the channel, but instead there will be regions of your fuel cell that will observe a lower concentration of oxygen, and consequently they will have a lower performance. Okay? This means that along the channel, the current density is not uniform anymore. the current density will be higher in this region because we have a higher oxygen concentration, and instead will be lower at the outlet because we have a low oxygen concentration. A low oxygen activity. Okay? Additionally, in the real world we have other effects because, for example, here we have a lot of water, which means that we can have condensation, for example. So by changing the stoichiometry, you are basically affecting a lot the uniformity of the operation of your fuel cell all over this surface. Okay? Okay, and you see that the most important effect is observed in the high current density region, where the potential really drops when you decrease the stoichiometry, going down here to the case 1.5, so the low values. Okay. Now, just this note just for the course, for the project of the course. If you want to simulate operating condition where the stoichiometry is lower than infinite, okay, that is what practically we need to do, you should use the 2D model, okay? But unfortunately, the 2D model takes a lot of time. This means that you could give your assignment probably next year if you use the 2D model, okay? In order to shorten this time, I introduced a simplification using the 1D model, but feeding not the inlet oxygen concentration, but instead an average oxygen concentration. Being the oxygen profile almost logarithmic, the most meaningful mean that you should perform is the logarithmic average. So, in this case, you can use the 1D model by feeding the logarithmic average of the oxygen activity between inlet and outlet. Here you see that the difference between the two models is quite limited. Okay, so it makes sense for you to use the 1D Galois-Stoic effect or 1D Holt-Stoic effect, that are the two models that give a result that is comparable with the one of the 2D models, but for sure requiring much less time. Now, how to change these options? For sure, you go in mode options, and you see here that there is one of them, and you can really choose 1D stoichiometry effect. Then you can run. I don't want to simulate a EIS. And I run my model. You see, first of all, that it solves. That's good. And you see that the speed, the computational time required is comparable to the one of the 1D model. Okay, so basically you can have quite fast results. Any questions? No? Okay. Question? No? Okay, I think we can have a break now. Okay? And then we talk about